let's talk about vectors. So, what even is a vector? I just hit something. What even is a vector, right? A vector is really a way to quantify a quantity that has a amount or like a magnitude, right? Like a size, like an amount, right? Like a magnitude as well as a certain direction. That definition by of itself is like, what do you mean direction? A good example of vectors can be found in like all of physics, right? This is a multivariable calculus video, or Calc 3 as the kids say these days. Not a physics video, but physics has a lot of quantities that have like a certain magnitude as well as a direction. Velocity, right? Your velocity has a certain like amount or a size, right? How fast you're going. 30 miles an hour or whatever. That's your magnitude. And it also is directed at a certain direction. I can be traveling 30 miles an hour north or west or 50 degrees below the horizontal. It has a certain direction. That is what a vector is. It's a way to quantify that. So, let's say, let me draw a vector. I guess I'll write it down. Vector is a quantity that has a magnitude and a direction. It has to have both in order to be a vector. So, this marker is crud. Let me get a better one. If I were to draw like an x or a y or xy, yx coordinate system, the way I draw a vector on a 2D space, it would look like this, right? So I can draw a vector that is labeled A. This is a two-dimensional vector. I'm labeling it A with a little arrow thingy on top of it to symbolize that it's a vector. And this is in 2D space, but hey, I can have vectors in 3D, even though this is a 2D. I don't know why. I can have vectors in 3D. I can have it kind of a vector coming out of the page. So the way I can draw that is with a coordinate system that has that extra dimension. So this is a xy coordinate system. I would just need to add a z, right, to get like that third dimension. That's not a vector. So I believe z comes out on top. Could be wrong. Correct me in the comments. But you can have a vector that is just directed in 3 dimensions, right? So for this vector, for a 2-dimensional vector, right, there's like kind of 2 components that make up the vector. There's going to be a component of the vector directed in the x kind of direction, whether that be left, right, depends how you define your coordinate system. If I define x to be left and right, I got a component in the x direction. That just means a component left and right. So, or at least, in this case, right. So this would be my x component, and my y component is going to be the one that's up top. So the way I can write, and let's say this component is like 3 units that way, and this component is 2 units up, right? So I can write I can write the vector as A equals, so I can do it as 3, 2, right? So this means 3 is a component in the x direction, and 2 is the component in the y direction. I can also write it as 3 I hat plus 2 j hat. So what are these I hats, j hats? We essentially have these unit vectors, right? This vector I is literally just this is what I hat is. It's a vector with a component 1 and 0. So x component is 1, right? And then the 0 component or y component is 0, so it's not going up at all. So that's I hat, and then j hat would be the opposite, right? 0, 1. So these are vectors that have, and we'll talk about magnitude. Actually, I should probably do magnitude first before I talk about this magnitude. What is the magnitude of this vector, right? We talked about vectors have a magnitude. Well, to find the magnitude, it's just the length of that vector. Like, that's how the vector represents magnitude. It's through the length. So I can say, well, the magnitude of a hat, or a, sorry, I mix those up sometimes, like with the tops, whatever. The magnitude of a is going to be square root 3 squared plus 2 squared, right? If you think about Pythagorean theorem, that's literally what I'm doing to find the length. Or in a more general form, it would be your first component squared plus the second component squared. And we're looking at 2 dimensions, right? So if you think about, well, what's the magnitude of I hat and j hat, it's just 1. So that it's just a unit vector, it just means it has a magnitude 1. If we're looking at 3-dimensional vectors, it's kind of similar, right? It's just a 3rd dimension, right? I can say if this is vector b hat would be equal to, we could have one component in the x direction, another in the y direction, and a third in the z direction, right? Those are the 3 components. I can also write it as a1 I hat plus a2 j hat plus a3 z hat. Whoa. Yeah, no, there's no doubt about this. Wait, what? Is it z hat? It's k. I don't know why I said z. It's k. K hat. K would be, right? Now I would just add on for the definition for 3D, it would be for I, it would be equal to 100. For J, it would be 010, and then for Z hat, or K hat, I don't know why I'm saying Z, I don't know where I got that from. K hat would be equal to 001, right? So now there's just 3 directions. And if you visualize, let me do a better job of visualizing this, like what a 3D vector looks like. Imagine you had like a box, right? If I had a box, kind of like so. Then I kind of had like, yeah, let me get this. Oh yeah. Let's say I had a box like so. Well, I could have a vector that is from if this is the left side of the box and this is the right side of the box, from this right corner to the upper left corner, like so, right? You can imagine that vector is going to be like, or I guess, how do I draw it? Oh, yeah, okay, I'll do another room example. So if I have a room like so, and you can try to visualize this. This is what we're doing. We're just trying to visualize what does a 3D vector look like. You could have from one corner, like if this was my room, I don't know if you can see me. If I'm standing right here and there's the opposite corner, like kind of directly opposite of me, I can draw a vector from this corner to that corner. Maybe I can call it B or whatever. I don't know. I can call it whatever I want. So B hat, or B, I don't know why I say hat. I see the little arrow on top and I just think hat. I see B, it's 3-dimensional. It's going, there's components to the left, or I guess to the right, going up, and then this way, I guess to the front, right? That's how a 3-dimensional vector looks like. And if I were to think about the components, well, if I were to think about the magnitude, let's just draw the components. There would be a component this way, component to the, I guess, up. That's an arbitrary word, I guess, in the z direction, and then a component in the y direction. So, if I were to do this, let's talk about, before I get to this, let's talk about vector addition. I guess that would help. How do you add vectors? Well, let's say I had a vector like so, a vector v, why not? And I want to add it. I want to add vector v with vector a. First thing to know about vectors, the starting point and ending point does not matter in terms of how the vector is like defined, like how vector v is defined. It doesn't matter where it starts or ends. I can draw vector v the same way as long as the direction and magnitude is the same. And by direction, in this case, it would you can kind of think of it as like the slope, right? If it's more steeply sloped, it has a different direction. It's angled differently from the vertical. So if I can move my vector around as much as I want, if I do say like, oh, there's a point P and a point Q, what's the vector between those points? I can also write it as PQ if I want. But if I have two other points, or let's do F and G, then V is going to equal FG, and I start with the tip letter F, and I'm going to following the direction of the arrow, and I get G. So FG would also equal PQ, right? Hopefully that makes sense, because yeah, I'm just shifting the vector around. So if I were to add vectors A and V, geometrically what it would look like is it would look like I'm literally taking the tip of A. So I'm doing what is A plus V. I'm literally doing V, and then I take A, and I take the tip and connect it to the, or I take the tail of A and connect it to the tip of V. And I draw, well then from the tail to the head, right? Like I draw that resultant vector, that would be A plus V. That's what it would look like geometrically. And if I were to think about it, mathematically, it's really the same thing as, so if A, it would really be the same thing. So A plus V would equal A1 plus V1, comma, A2 plus V2. So if there were, so I would add the x components of the two vectors, and then that would be my x component for the added vector, and then the y components, I would add them together as well. Yeah, that's how I go about doing a good old vector, right? Like that's what vector addition looks like mathematically or geometrically. And so with that line of reasoning, and for subtraction, I would literally like flip A. I guess I should talk about scalar multiplication first. For that, if I take a certain scalar quantity, that's just a quantity with no direction, it's just magnitude. An example would be speed. If I take A, right, let's go back to A. If I take A and I multiply it by 4, right, I get 4 times that vector. All that means is that the magnitude will have increased by 4. So, the magnitude will have increased by 4. That's just the same thing as multiplying each of these like things by 4, like each of the components by 4. So that would be the same as 12 and 8. Why? Well, think about it. If you have that vector A, and then you have, I guess, let's generalize this. So we have like A1 I hat plus A, and this is A2 J hat. Like those are the vectors. So if A is equal to A1, A2, right? Then if I were to multiply the magnitude by 4, that's the same thing. So if I were to multiply the magnitude of A by 4, that's the same thing as putting a 4 on the left side of 3 squared plus 2 squared. And then that's going to be the same thing if you put the 4 inside the root. That's just 16. You can also think about it as similar triangles, but that's lame. Algebra is the best way to do anything. That was sarcastic. 16, you have your 3 squared, or I should generalize this, A1 squared plus A2 squared. And then that would be the same thing as distributing the 16 to both And then you can see, as clear as day, then, oh, you just put the 4 in the squared thingy-mabob, right? Like, that would now become 4a1, right? So I'm just multiplying each component by that scalar quantity. If I make it negative, it literally flips it. So 1/2 a would look like, so if I have, I'm running out of space, goodness me. So if I have, this would be a, right? And then I could have 1/2 a, like 1/2 the length, right? I'm literally, the magnitude just becomes 1/2 as much while maintaining the direction. That kind of makes sense, right? Because scalars don't have direction. How can a quantity that doesn't have direction affect the direction of a vector when they're multiplied? Hopefully that's kind of the reasoning that you kind of thought of, or make that make sense when I explain. I don't know. But if I make it negative, it just flips it around. So negative a, how would be like that? Well, hey, a minus v is the same as a plus negative v. So I would just take negative v, which would be like so, and then I just do tip to tail if this was a, right? I'm running out of space, but if I have a, and then negative v would be like that, well then I get this a minus v would look like that. And if you try to think about why would that make sense? Yeah, okay. So now back to finding the length of one of these things. Well, we know that if we add the x component and y component vector using tip to tail, right, I would get a vector like so. So if this is a room, this added like, so let's actually do it like this. Let me restart this whole room thing and we'll conclude the video with how to get that vector. So think about a room, your room, any room in the world, it's fine, whatever room you think of. Hopefully it's a room with a lot of happy memories. I'm gonna draw my walls. And let's say we'll call this the, so let's first of all, how much time am I at here? I want to see 17 minutes. Wow. Let's finish this video with this problem. Let's just define like some direction so that we're on the same page of what means what. I'm the architect of this room, so I'm just going to say that, hey, this edge right here is, I'm going to call the left side of the room. I'm going to call this side the right side of the room. I'm going to call this edge the front of the room. This is going to be my back, and then this will be the top of my room. And over here will be the bottom of my room. So those are just some terms that I'm going to use to describe this room. So let's say I want to find, let's say we have a corner on the front top right side, on the front top right side. So front top right side of the room, and I have the corner on the opposite side. So it would be the back left bottom side. What is that distance in terms, like, and what would that vector be? We'll call that vector v, or I call that vector s. Why not? So s. So the dimensions of this room. Well, first let's kind of think about this. What would, if let's say F, L, and R represent the dimensions of this cube, I can kind of say that S, and let's use, maybe we could use beta for bottom or something, and then B for back. So S, the vector S, would really just represent the X direction, which I will call, it's from left to right, and then this dimension I'll just call, well, that's confusing, whatever. Well, the X direction component is F, just based off how I drew it, or B. And let's define my axis like so. So we know what's positive and what's a negative. So Y, X, Z. So front would be my X component. My Y component would be T for top. And then my Z component would be, if I'm thinking about, oh, sorry, I'm so sorry, my Y would be L or R. Doesn't. I'll say R. Why not? Because R, like it's the front left, and then we'll say t is top for the z component. So with that said, let's think about what would the length, or what would this distance be, the length of that vector. So another way to really write this is fi hat plus r j hat plus t k hat. So I j k, yeah, okay. So if we think about f I hat is right here, and then L would be L J hat would be right here. If I'm adding these two vectors, F I hat is directing the x direction, L J hat's in the j direction, then you could think about, well, if I were to add those, I would do tip to tail. So I would take this vector, put it here, and this would have the same, like they're parallel because it's a rectangle, so same direction. So this would also be L J hat, and then I just add those vectors. So this vector right here is now in the diagonal of the room. So if we were to think about slicing this room in half, kind of like so, and draw, if you think about slicing it in half and thinking about that vertical plane I just kind of drew there, let's draw the vertical plane. We would now have a vector like so, which would be fi hat plus the new added vector fi hat plus rj hat, and then I would have my actual s vector, and then this upward edge would be t k hat. So the length of s, if this is a right triangle right here, the length of s would be, so the magnitude of s would be equal to the square root of the magnitude of fi hat plus rj hat squared plus the magnitude of tk squared hat squared. But the magnitude would just be t, right? Because k is a unit vector, so that length would just be t. So plus t squared. Maybe you can see where this is going. All right, what's the magnitude? Well, now we just got to find what is that magnitude. Well, that magnitude, right? The magnitude of t I hat squared, or fi hat squared plus rj hat squared would be equal to this, well, if you think about Pythagorean theorem, I don't have to do the square root, I'm just doing square. So that would equal the magnitude of fi hat, which is just f squared, right? So it's just Pythagorean theorem. F squared plus L squared. So substitute that back in here, you just get the length of that vector. Just be equal to square root f squared plus r squared plus t squared. And I used L interchangeably. I'm sorry about that. This really should be R. But yeah, that's an intro to vectors. I'll make another video talking about dot products, cross product, whatever we need to know for actual Calc 3 stuff. This was just kind of a review. So yeah, thank you for watching. Vectors are pretty cool, right?